Alright everyone, this is Jason from organicchemistoncall.com again. What I'd like to discuss today is a different way of looking at functional groups in organic chemistry. So this is not all the functional groups that you're going to come in contact with, but this is going to be a majority of them. And what I want to show you here is that you can use electronegativity and you can use the carbocation stability behavior or carbocation trend to figure out which way these functional groups will react. So let's go through these. So the first one I want to look at are the alkyl halides. Now let's just imagine, or first let's look at it this way. We know bonds are just a pair of electrons. What if we broke that bond and took those two electrons and dumped them on one of the two atoms? So in this case, if we have an alkyl halide, we could take the two electrons and dump them on the halogen, and the reason being is that the halogen is more electronegative than the carbon. So when we dump those and break the bond and move the electrons in that direction, since electrons are negative, the bromine is going to be negatively charged, and therefore the carbon is going to be positively charged. So we can see from this vantage point, we can see that the carbon has a carbocation character, therefore would act as an electrophile, so something would attack that, meaning a nucleophile. Now if we go to the alkene, or the double bond, we'll notice here that we can't base this off of electronegativity values because both of them are carbons. So what we're going to have to do here is if we take the electrons, let's say in the first one, and we decide to break one of that double bond and move the electrons on the carbon in the middle, that's going to generate the negative charge on the middle carbon. We can imagine if we looked at the bottom one, we could take those electrons, break that bond, and push them on the carbon on the right. Now since the electronegativity values are the same, what we're going to have to base this off of is carbocation behavior, or the trend. So we're going to see here that the bottom one is going to win out or be favorable, more favored, because of the trend. So we know that carbocations tertiary is more stable than secondary, which is more stable than primary. In this case, we get a secondary carbocation. So that's going to be the behavior or the direction that we want to think about with the alkene. Now we'll see in this case, this is different than the alkyl halide, where we saw the alkyl halide was acting as an electrophile. The double bonds, we can think of them as acting as both an electrophile and a nucleophile because we both have a plus and a minus. Now when we switch to alkynes, we can imagine this is going to be very similar to the alkenes. Now what we're really going to want to pay attention to is when we're dealing with alkynes, we want to know if we're dealing with a terminal alkyne or an internal alkyne. And the only difference that we're going to be looking at is with the terminal, one side of the triple bond has an H in the terminal, and the internal, both sides are carbon. Now we'll see here in a minute why that makes a big difference, but what we're going to determine is it's really that the terminal alkyne is the one we're going to have to pay attention to. Now if we looked at the internal alkyne, we did the same thing that we've done so far, is we take one of the bonds and we break it and we dump those two electrons onto a carbon. We'll see here on the bottom right hand structure that we get a minus charge and a plus, but both of those carbons are secondary. So with an internal alkyne, we typically don't have to worry about which side the minus or the plus is going to fall on. However, when we look at a terminal alkyne, we can see that when we do take those electrons and push them to one side or the other, in the case in the bottom right-hand structure, we'll see that if we push our electrons to the right-hand carbon, right side carbon, that we're going to get our negative charge, and that's a quote-unquote primary carbon, whereas if we look to the left-hand side, that's a secondary, and that's where we would want our positive charge to fall due to carbocation stability. The last one that I want to look at here is a carbonyl compound, and this one we can base it off of electronegativity. So we can take the electrons and we can dump them on the oxygen due to the fact that oxygen is more electronegative than carbon, and in this case we get our positive on the carbon, so our carbon is going to be an electrophile. Now if we think about this in terms of our alkene, we said that since we have both a plus and a minus, it can act as a nucleophile and an electrophile. Now although this is true, in most undergraduate organic chemistry classes, the focus is not on the oxygen minus as a nucleophile, but it's on the carbon and electrophile due to the fact that organic chemistry is based on forming carbon-carbon bonds. So at this point, just focus on the fact, or you can think about carbonyls as being electrophiles. So if we just sum this up, we've talked about alkyl halides or electrophiles due to the fact that the carbon is positively charged. Double bonds or alkenes or electrophiles and nucleophiles because they have both a positive and a negative. Our carbonyls, I put them side by side because you can kind of think of that as an alkene, quote unquote. But we can think of that specifically as an electrophile because in the carbonyl we don't worry about the O minus. And when we look at a triple bond, we can think of that as both being electrophile and a nucleophile due to the fact that we can have a both positive and a negative value.